Okay, so now we're going to have a look at a mathematical induction problem that involves derivatives. Okay, so we're going to use mathematical induction to prove that the nth derivative of x squared e to the x is going to be given by this expression: x squared plus 2nx plus n times n minus 1, all multiplied by e, where n is going to be a positive integer. Another way I could ask the question is, if f of x is x squared e to the x, we want to prove that the nth derivative of f is x squared plus 2nx plus n times n minus 1 times that quantity times e to the x, for n being a positive integer. So let's work through this problem together. Our basis step is if n equals 1, because we're working with positive integers, if n equals 1, our derivative of x squared e to the x is going to be, using the product rule, x squared times e to the x plus e to the x times 2x, right? First derivative of the second plus second derivative of the first. And if I look to see if I can factor this to kind of have the form that I have there, this is going to be the same thing as e to the x times x squared plus 2x plus 0. So therefore, our left-hand side equals our right-hand side, and we're going to be true for n equals 1. Okay. Then our inductive hypothesis. We're going to assume true for n equals k. Therefore, we're going to say that our nth derivative of x is going to be given by, and I'm just going to rearrange to put the e to the x in the front, e to the x times x squared, and it's not going to be the nth derivative, it's going to be the kth derivative. Want to be careful. X squared plus 2kx plus k times k minus 1, where k is going to be some positive integer. So that's our inductive hypothesis. Okay. Then, after assuming true for n equals k, we're going to consider when n is equal to k plus 1. All right. So when n is equal to k plus 1, that's going to be our k plus 1 derivative. So that's going to be our derivative with respect to x of our kth derivative, which is going to be our derivative with respect to x of e to the x times x squared plus 2kx plus k times k minus 1. And we're going to need to use the product rule here as well. So if we're going to use the product rule, our derivative is going to be our first, e to the x, times the derivative of the second. So the derivative of x squared is 2x, derivative of 2kx is 2k, and we have a constant, so that's 0. And then plus our second term, that's x squared plus 2kx plus k times k minus 1. And we need to multiply that by the derivative of our first, which is simply e to the x. Now let's group some terms. So we can factor on e to the x from both of these. So that's going to be e to the x times 2x plus 2k plus x squared plus 2kx plus k times k minus 1. Okay. So I'm going to group a little bit more, maybe some distribution, because I'm going to try to show that my derivative is going to be this, but instead of a k, I'm going to have a k plus 1. And then instead of a k, I'm going to have a k plus 1. And instead of a k minus 1, it'll be k plus 1 minus 1, which would be k. So I'm just going to rearrange this a little bit and kind of keep my eye up here for how to make that a k plus 1 and how to make this a k plus 1 times k. All right, that's what I'm trying to get to. So work through, I've got x squared, so the x squared stays. That's good. Then I have a 2x and a 2k and a 2kx. So I'm going to factor out a 2x from what I have. And so I'm going to have plus 2k or 2x, excuse me. I'm going to have factor out a 2x, and that's then going to give me a 1 plus k. Right? And that's once again coming from looking at this term and this term. Then I'm going to go ahead and multiply out what I have with my k. So I have plus 2k plus k squared minus k. So that's going to be e to the x, and I'm going to rearrange this so that's x squared plus 2x times k plus 1 plus, and I'm going to have, let's see here, k squared plus k. All right, so that's almost to what I want to have, right? And I'm just going to rewrite this so it looks exactly like what I want it to look like. So that's e to the x. There's going to be no ambiguity that I am equal to what I'm trying to show. So e to the x, x squared plus 2 times k plus 1 x plus k plus 1 times k. So therefore I am true for n equals k plus 1. Then all that's left to do is put in my conclusion statement. All right. So since p sub n is true for n equals 1, and when p sub n is assumed true for n equals k, it follows that p of n is true for n equals k plus 1 by the principle of mathematical induction. Our statement is true for all positive integers n. All right? So in other words, we know how to find our nth derivative for our particular function. All right, so once again, mathematical induction show that our nth derivative is given by a particular value for all positive integers. And another way that we could state the same, do our basis step, do our inductive hypothesis, consider our k plus 1th case. In this situation, the k plus 1th case is going to be the derivative of the kth case. So the k plus 1th derivative is the derivative of the kth derivative. Go through, do our mathematical work, and thankfully the result holds. And so we have our final statement that if our proposition is true for our first case, and when our proposition is assumed true for our kth case, it follows that our proposition holds true for the k plus 1th case. Then by that mathematical induction, our proposition must be true for all of our considered values, in this case, all positive integers. So an example of working through a mathematical induction involving derivatives. Thank you very much for your time.